Solar power. There are two ways of gaining energy directly from the sun. One is using solar cells or photovoltaic cells to transform the light energy directly into electrical energy. The other is to use the thermal energy by raising the temperature of something, generally water. At the heart of the solar or photovoltaic cell are two pieces of semiconductor material. These are made mainly of silicon, but the N or negative type here is contaminated or doped with a tiny amount of phosphorus atoms. Though it stays neutral, there are a small number of electrons which are free to move around the structure. These are called free electrons. The P or positive type here is contaminated or doped with a small amount of boron atoms. This has a lack of electrons, leading to spaces or holes. These act as if they're positive charges that are able to move around and carry charge. When the two pieces of semiconductor are brought together, this happens. The electrons close to the boundary have jumped across into the holes. This leaves the N-type having a slight deficit of electrons, and so it is now positively charged. The P-type, having gained electrons, is negatively charged. And so a potential difference of voltage is set up. This then prevents any further electron movement. An electron here, for instance, would find it difficult to move from a positively charged object into a negatively charged object, and the electric field will cause electrons to be forced this way. So the electric field will push electrons towards the N material, which is now positively charged. If a photon of light is absorbed by an electron, it can free it from its hole. If the electron is close to the boundary, the electric field will send it to the N side. If the two sides are now connected by a conductor, like this, the electron will travel back to its hole on the P side, like this. We now have an electric current. Just to stress at this stage, you are not expected to know in detail the operation of a solar cell. One solar cell can only produce a maximum EMF or electromotive force of about 1 volt, but by placing several in series, the EMFs add. So here a 1 volt cell with 4 of them in series can produce an EMF of 4 volts. This incidentally is the circuit symbol for a solar cell. One problem with solar cells is that they do have a very high internal resistance of around 1 ohm, meaning a maximum current for these arrangements, given by Ohm's law of current is equal to potential difference over resistance, of just 1 amp. Here we have 4 solar cells in series placed in parallel with another 4 solar cells in series. This arrangement will still give an EMF of 4 volts, but now with half the resistance, and so twice the current. For any solar cell, the greater the light intensity, the more photons there are, and so the more current. But as photon energy E is equal to hf, where h is Planck's constant, and f the frequency of the light, the lower frequency photons will not have enough energy to free electrons, so we cannot make use of this part of the sun's spectrum. Some of the light will simply reflect off the surface of the solar cell. Silicon is a shiny material, but it is given a black coating to limit this effect. There are no moving parts, and so there are no losses due to friction, but there will still be electrical resistance losses, which will cause heating. Solar cells, therefore, can only achieve efficiencies of up to 20%, but this can be acceptable as the energy supply, i.e. the sun, is free. Let's look at an example. If the intensity of the sun's radiation is 500 watts per square meter, calculate the area of solar panel needed to provide the energy for a 100-watt light bulb if the panel has an efficiency of 15%. Well, from the datasheet we find that intensity is equal to power divided by area, and so rearranging, the area is equal to power divided by the intensity. The power we need is 100 watts. The intensity we have is 500 watts per square meter, but only 15% or 0.15 of that, meaning we need an area of solar cell of 1.3 square meters. Using a circuit something like this, with a voltmeter placed across our solar cell and an ammeter in series with a variable resistor, we can find the characteristics of the solar cell, or the current and potential difference it can provide at various different light intensities. This graph shows the characteristics for a typical cell, and this line shows the characteristics at a light intensity of 700 watts per square meter. A higher light intensity would give more current and a higher voltage. This is a line for 1000 watts per square meter. You'll see for both lines we get the maximum potential difference when zero current flows. As the size of the variable resistor is reduced and the potential difference reduces, the current will rise to a maximum, but then it stays at roughly the same current all the way down to zero potential difference. If we want to find the efficiency of the cell at an output of 14 volts and a light intensity of 1000 watts per square meter, that is 14 volts, 1000 watts per square meter across at 8 amps. Well, we know that electrical power is equal to current multiplied by potential difference, which in this case is 8 amps and 14 volts, giving a power output of 112 watts. Efficiency is equal to useful power output divided by the input power, which in this case is the 112 watts we're getting out, divided by the 1000 watts we're taking in. This is taking a 1 square meter solar cell, gives an efficiency of 0.112 or 11.2%. Another way of getting the sun's energy is through solar heating. This is used to raise the temperature of water, and generally another method, for example a gas boiler, would be available to raise the temperature of the water further if necessary. Energy is saved by not having to use gas to raise the temperature of water all the way. A solar panel would be placed on a south-facing roof, gaining maximum energy from the sun. A glass panel on the top, coloured black, will absorb the maximum amount of radiation from the sun and prevent some of the radiation escaping. A pipe containing glycerol passes through the solar panel. It would have many turns inside here to maximize the surface area and so maximize the energy gained. As the glycerol passes through the solar panel, its temperature rises. It then comes down here, passing through a heat exchanger in a hot water tank. This again has many twists to maximize the surface area and so maximize the amount of energy exchanged to the water. As the glycerol passes through the water tank, it will cool down, and a pump here will pump it back up to the solar panel to carry on round again. The pump is necessary, otherwise the raised temperature glycerol would be less dense and so would rise to the top here and stay there. These solar heating systems are becoming more common in the UK.